Alright, so I thought I would do this on my desktop here instead of on the notebook because I wanted to talk a little bit about the next section, which is regression. And so I need to get some pictures, and I also wanted to talk about the homework. So um, that's all on the uh, paperwork here. So um, first off, I just wanted to mention the confusion matrix. So this is a good way of talking about the error in our classification. And I think we talked about this last time, so I won't spend too much time on it. But I just wanted to show you the image of the confusion matrix. This is kind of a nice picture. We usually just end up having a matrix. So along the diagonal here are the actual accurate values, right? Because, for example, the actual dog was classified as a dog, actual cat classified as a cat, actual rabbit classified as a rabbit, and so on. Good. And so, yeah, and then you could kind of go down each column if you wanted to, right? Because out of all the dogs, right, the dog was classified 23 out of, let's see, is that 34, 38, 23 out of 38. And so that's a pretty good number. And so you could, similarly, you could see the cat as being misclassified the most. And so this confusion matrix is a nice way of seeing what the error actually is doing in your graph. Good. So what we want to talk about today is k-nearest neighbor regression. Okay, so I'm going to flip over to my document camera here so we can take a look. So what is k-nearest neighbor regression? We'll just kind of picture it in the plane, and suppose, you know, I've got some domain points here with some range points, right? And so now the question is I come in, I say, okay, here's my new value of x, right? And I'm wondering, what should my new y be? And so when we're taking our nearest neighbors, right, in this case, let's say I've got the 4 nearest neighbors, so I'm just, remember this measurement is going to be taking place in the domain, right? And so in this case I have 4 nearest neighbors, and so then I have the 4 corresponding y values, right? And so probably the most natural thing to do then is to say, well, I'll just take the average. So let's say that's y1, y2, y3, and y4. And so my unknown value of y, let's see, where will the average be? About here. And so I'll say that this value then is going to be my new y. And again, that was computed by taking the sum of the yi's, right, and dividing by 4. So you're taking the average. Good. And then you can just slide the x down, right? So now if we have a new x, you know, you could take your neighborhood around that. I guess we're using the 4, so, and so on. And so you could just slide this down. Good. Now I should say that there is a different way of doing that. And the different way of doing that is, instead of just taking the yi's, right, what we're going to do is we're going to weight the yi's by distance. Okay, and so oh, wait a minute. Um, let's think about that. So I want the lowest value. Yes. Let me pause that for a second. All right, so I paused that for a second because what I would like to do is I would like to weight the points that are closest more heavily than the points that are far away. And so in the notes, you'll notice that I said, well, let's take our di, the distances, right, and what I'll do is I'll divide by the sum of the distances, dj, j equals 1 to n, right? And so what happens then is you end up changing the distance. So instead of having like d1, d2, and d3, for example, if you only have 3 neighbors, you change that to be d1 over d1 plus d2 plus d3, and then d2 over d1 plus d2 plus d3, and so on, d3 over d1 plus d2 plus d3. And the nice thing about these, right, if I call this like alpha 1, alpha 2, alpha 3, is that each of the alpha i's are between 0 and 1, and the sum of the alpha I is equal to 1. And so they act like little probabilities. And so this is a nice way of getting some weights for well, not just a distance measure, but for anything. The problem is, do you see how this isn't going to do exactly what I wanted here? So I have to change that a little bit. And so I'll change the notes. But instead of di, right, this is going to be the smallest when it's closest to x and largest when it's away from x. So I'm actually weighting the larger values instead of the closer values. So I need to change that. I should probably have 1 over di, right? And then 1 over d1 plus 1 over d2 plus 1 over d3, for example, if I only had 3. Because 1 over di is going to be the biggest, right, when di is the smallest. And so I should change my weights to be like that. Good. So I'm glad I talked this through with you guys. So we want to change the weighting. So the weighting that I see in the notes that's incorrect, we're going to make the change here. Is right here, right? This should be 1 over di and 1 over dj. And so I'll make that change before I post it tonight. Good. And then what we'll do is we'll take our weighted average of the targets. And so the reason I'm kind of being careful with these alphas is that I don't want the TIs to be outside of the range of the other targets, right? Because the other targets are, this target should be within a reasonable amount, right, of the other targets as a way of interpolating through that. And so, yeah, what happens is that if you have a sum like this, it's kind of interesting as a side note. Instead of a linear combination, we would actually call that a convex combination of weights, or of the targets. So convex combination means that you're taking a different set of coefficients. The coefficients sum to 1, and they're all non-negative. Good. And so, yeah, we can take a look at the code here, or at least some examples. I think my examples may be wrong, but I'm going to have you work through them too. So here's some examples of some data. So this is the output of a one-dimensional regression, and we're going to predict bone marrow density given age. And so the black dots here that you see are the data points, and the red line, or the red curve here, is when we just use one nearest neighbor, and the green curve is what you would get if you use 3 nearest neighbors, and the magenta dotted curve here is the curve that you would get for 7 neighbors, and the blue curve is what you would get for 20 neighbors. So what do you see in terms of the variation, the amount that the line wiggles, right, as you increase the number of neighbors? Yeah, we see that the graph stops varying so much, right? The more neighbors you have, the smoother the curve that you get. And so what's happening here is something called the bias variance trade-off. So by bias, we mean something with high bias has lots of variability. And so we want to, let's see, yeah, it's always a question as to whether you want something, how much bias, how much variance you want in your model. Um, because you can see, right, if you could increase the neighborhood size or the number of neighbors that you get by a lot, you're going to be getting something that's close to a line. And then finally, if you make your neighbors big enough where you're encapsulating basically the entire data set for every point, then that's going to be just a constant straight line. Yeah, it's not even going to vary because you're always going to be outputting the same thing when you do that. Um, so those are kind of the extreme cases. So typically you don't want to do anything in the extreme, right? You want to try to find something between the two extremes. So you want to get something smooth enough so that it generalizes well, so you get the general idea or the general model without modeling the noise. But you still want to capture the overall, your models should be complex enough to capture the phenomena that you want, but it shouldn't be so complicated that it starts modeling the noise. And so we have to be careful about that. Good. And so this is the average. I think I see what's the, yeah, I need to change this graph a little bit, right? Because it looked like the weighted values were giving me more variation. I think that was because I was weighting the data points that are outside of the neighborhood, or the farther away the data points were, the more weight we were giving them. So I'm gonna have to change that picture. Uh, but yeah, we'll look more closely at this example. In fact, we're going to do a problem like this, not quite this example, but one that's similar. Good. All right. And so now I'm going to pause and switch gears a little bit, and we'll talk about homework. All right, so what I'm going to do is I've written up some code for you, and it does various things. For example, I've written a little piece of code called conf matrix, so it builds a confusion matrix. And so the idea is I'd like for you to take a look at that code. In this case, we'll take a look at it real quick here. Take a look at the MATLAB code there and see if you can figure out how to use it. In other words, the confusion matrix, you give it a vector of actual values and a vector of predicted values and the number of classes in your problem, and it outputs the confusion matrix in matrix C and the error vector in error, ERR. And so this way you can take a look to see what the overall error is. You can kind of see it here. Or you can just give out the values in the confusion matrix. And so that's very nice to know. And by the way, you can check to see how I actually compute the confusion matrix if you want. Good. And so that's one helper function, is to build the confusion matrix. So once you've built your classifier, right, you would call the confusion matrix to visualize the results. By the way, in Python, that's a built-in function, or a built-in, what do you call them? I'm blanking on the word. I don't use Python that often yet, but yeah, it's in sklearn.metrics.confusion matrix. So go ahead and check that out in the documentation. Good. So fitknn is a program that takes data in and outputs the predicted classes using the k-nearest neighbors. And so the version in Python is sklearn.neighbors.kneighbors classifier. Yeah, I'm not going to be using too many options. The Python version has lots of options. Basically, we want to try to find a way of extracting the error on a test set. So what I want to do is I want to put my data matrix into fitknn and my test set, and I want the function to output the error on the test set, right, using whatever nearest neighbors. Let's see if I can find that real quick. I'll pause and find it. Okay, here it is. So predicted classes equals fit KNN, and then this is your data that you're building the classifier on. T is the set of targets, and the hatted X is your test set, and you're using N nearest neighbors. And so down here you can see what's happening, right? I'm just taking X hat for each of the columns, and I'm subtracting it from my data. I get my distances. You don't have to do anything with this, by the way. It's just this is how the algorithm is working, right? This is probably the reason why I didn't want you to have to write this. It's kind of yeah, you're trying to find the number of times each class appears, and so that can be kind of a pain. You can check out the code, but mainly I just want you to be able to call this function. Okay, and so we just call it fit KNN, XT, X hat, and N, and then it outputs the predicted classes. Good. So there's not much more that you need to know about that than that. Um, Let me pause and get back to the other page. Good. So now we have some other commands that we want to be able to use. K-fold cross-validation. So this is going to split your data up for you. So you give it your data and your test set. Wait a minute, not your test set. You give it the data set. Well, actually, you don't even need to give it the data set. Let's take a look at that one. I just want to check that because my k-fold CV is a little bit different than Python's. Python's is actually going to just put out indices, and my function, my version of the function actually puts out the data set itself. So let me pause that. Yeah, here we go. So it is just the data and a test set, and then the number of points in this case. And so yeah, I should say n is actually the number of folds, not the number of data. Now it's important to know which direction your matrix should go, and unfortunately I think I kind of like using dimension by number of points, so the matrices tend to be wide, but I think Python is the opposite. So be careful about your dimensions. Be sure that you know which dimensions you should be putting in. So that would just be, you might have to transpose these if you need to. Okay, and so this is telling you what you're going to get. What comes out is this data structure called data, and there's a number inside there called num test sets, and so that's the number of folds. And so then you just, if you go through a loop, you can extract each of those. Like this is the training set and the training target set, and then the test set and the test target set for fold number 1. And then you go through and you can extract it for fold number 2, and then you can extract it for fold number 3. So once you get train and target, right, and your test, then you can do the nearest neighbor on each fold, right? And then you can get the average error after doing that. Good. So again, k-fold CV just pulls this data set X apart, and it's going to be doing so randomly. So that's what the rand perm down here does. It's going to randomly resort the data in X and T. It'll be consistent. Good. All right. And so again, this function does not have to be touched. You're just going to be using it, so you're just going to be calling it. And that's only if you're in MATLAB. If you're in Python, we already have the Python is a built-in one. And so instead of just giving you the name kfold, I went ahead and did a full example here. So you might pop this example into Python just to see what gets output and what is input. Some other things, standard scalar is kind of nice. I saw that in the Python code, and I thought that might be nice to have as a MATLAB function too. And so we went ahead and wrote up a quick piece of code for that. That just scales your data. And then of course we have a standard scalar in Python. That's in the scalar and preprocessing section. And then another piece of code that was kind of nice that I saw was train test split. And so this just takes in a data set X and your targets T and splits it into training and testing. So it's different than the cross k-fold stuff. This just splits it into two, actually four, because you have X train and X test. So the X is broken into two. And then your outputs are also broken into train and test. Good. Um, yeah, that's all the functions. Let me pause now and bring up the homework. Good, so I won't go into this in detail. You can read it yourself, but I just wanted to mention what we're doing here. We're going to be in groups and we're going to be working in data, and I want you to do a k-nearest neighbors classifier and a k-nearest neighbor regression, and you'll have two different write-ups. You'll have one write-up for the k-nearest neighbors on the Fisher's iris dataset, and you're going to have a k-nearest neighbors for a regression problem. Yeah, I'm going to be giving you the data for that. It's not really a real data set. Oh, well, we might try a real data set later. I just wanted you to see that first. The thing with the regression is, instead of a confusion matrix, we'll be using something called the coefficient of determination, or R squared, to figure out a good way of seeing how good our fit is for our function. And so the way to compute that is, if you have targets T and model output Y, you can go through these computations here and find the R squared. And so the R squared is going to be a number between 0 and 1, and the closer to 1 you are, the better the model. So you could think of it as R squared is telling you how much variance in the data is being explained by your function. That's one way to think about it. Okay, but we'll talk about that again. So I'm giving you a full week for this. So what should you do? So first of all, I would try to get the code together. So take a look at Fisher's iris data. Now, what are you going to do with this data set once you get it? Well, your goal is, let me bring up the paper. So your goal is to have something like this. It's a lab write-up, and so yours would be Fisher's iris data, and of course you wouldn't have sample write-up. You put your names there, put the date. Now I'm writing in LaTeX, and I'll put the LaTeX file up on the class website, but you do not need to use LaTeX if you don't want to. You can use Word or whatever word processor you feel comfortable with. Mainly I want to just focus your attention on the sections. So section 1 is just a discussion of the problem. Section 2, you want to talk about what the data is. And this is really important because it's going to be guiding your thinking. This is a good way to think about it. Whenever you're given a data set, you need to be able to explain what it is. Usually we don't have this much detail, but at least be able to explain how many, what the dimensions of your data are. And then also down here we're showing you the mean and the standard deviation for each of the 8 variables that we have in this data set. So you can read through this. You're going to do something very similar for Fisher's iris data. That's your goal. And so notice here that I even did a principal components projection to the first 2 basis vectors. And so that's always a good thing to show. And that shows that there is some separation, right, between the 2 data points, or data sets, the 2 classes I should say. And so we have some reason to believe that there's something there that we can classify. And then you're going to perform a 5-fold cross-validation to determine the best number of neighbors. And so yeah, I found out that the best number of neighbors in this example was 23. You can see it down here. And so I was computing it for, let's see, 3 to 35. And by the way, the graph doesn't always look like this. for this five-fold cross-validation, there is some variation in this curve. Um, so I did it several times just to see what the variation looked like in the curve, and then I kind of settled on this picture for the best one. And then finally, you want to just briefly touch on the results. And so here I showed the confusion matrix for this set. Okay, and then include any references that you might have. And then finally, insert your code here. And so you don't have to put the stuff that I provided. This is mainly the driver code, right? The one that says load iris data and then do some kind of principal components and then do the five-fold cross-validation and so on. Good. Um, so for now, think about how you're going to use the 6 helper functions to put together a very close version of this paper, except for the Fisher's iris data. Okay, and so you might give yourself an early deadline for that, maybe in 2 or 3 days by the end of the week. See if you can get some sample code together, and if you're still having problems with that, we can get together. I can get together with your group, and we can talk about it. Um, Especially if you don't have a lot of programming experience, we'll try to put it together. I can give you some pointers. Good. I think I've talked too long today, so